Hi everyone. Today we're going to be going over a brief overview of the origins of astronomy. So how did we get to the astronomy that we have now that we're learning in this class? I apologize in advance. This video is going to be a bit longer than normal. That is because I am trying to shorten the entire history of astronomy into about 50 slides. So today you will learn about first principles, and which were used to explain the universe in the beginning. We will learn about parallax. We will be able to compare and contrast Aristotle, Ptolemy, Copernicus, Kepler, and Galileo, and all of their views and discoveries. And then we will go over Kepler's laws and how they explain orbits, orbital speeds, and timing of orbits. And be able to list the advances made by Galileo. And then lastly, we're going to go over Newton's laws, how he came up with them, how they can be applied to planets and or moons. So to start, a first principle is something that is considered to be true, something that's considered to be so obvious that it's true, must be the way that things are. So we would consider this something that was relied on before the scientific method was possible. So before we had the ability to collect data and make observations and do tests on a topic, people would trust these first principles. So for example, in ancient Greece, the Earth's place in the universe. So there was no way of testing or studying or proving Earth's place in the universe, so they went by their first principle, was that the Earth must be in the center. So not all of the first principles were correct. So, for example, Earth's place in the universe. Ancient times, they didn't have the same technology and understanding that we do now. So there have been a lot of things that were originally first principles considered obvious because, of course, that's how it is. Things rise in the east, set in the west, must be rotating around us. Now that we have more data and more understanding, we learn that that is not actually true. So a little timeline and the main people that we're going to talk about today. We'll start with Aristotle and Ptolemy, and then jump a couple thousand years to Copernicus, Tycho Brahe, Kepler, and his laws. Then comes the invention of the telescope and Galileo, and then Isaac Newton. So we're going to go over all of these people and their understanding. So I should note that these are the main people that discovered or made advances in astronomy the way that we can think about it as simply as possible. But astronomy was going on all over the world, so these aren't the only astronomers that made large discoveries. These are just the first that we have documented evidence of, or the first that made these discoveries and then were able to share them and teach others about it. So, Earth's place in the universe was originally thought to be in the center. So, it was thought that Earth was in the middle, and everything above Earth rotated around us. Everything above was considered the heavens. So, this is in a very, very, very long time ago. In everything around the Earth, meaning like all of the celestial sphere, was considered the heavens, and it rotated around Earth. So it was understood that Earth was at the center of 55 different spheres. So the different spheres were rotating at different rates and different angles, and each sphere had a planet or the moon or the sun. And then everything outside of those specifics was called the heavens beyond. So it was as if there was a real celestial sphere, and all of the stars were on that one outer sphere. So these were all very perfect geometric circles. And this is because a Greek philosopher called Plato had the understanding that the heavens are perfect, and the most perfect shape is a circle. So everything about the heavens, or outside of Earth, had to be these uniform, perfect circles. So this idea was accepted for about 2,000 years of astronomy, was that Earth is in the center, everything is rotating around Earth in perfect circles. So the main reason that this could have made sense, or did at the time make sense, was that if Earth was in fact moving, especially relative to the stars, we would see something called parallax. And because parallax was not observed, that means Earth must have been stationary. Earth must be stationary because we don't see parallax. So parallax is the apparent motion of an object due to the observer's motion. So if Earth was moving, we would see an apparent motion of stars and planets. So it's similar to, here we go. If you have parallax between your left eye and your right eye. So if you look at something with your left eye and then covering your right eye, and then you switch, so you're looking only through your right eye, things will have shifted. So you see a change in position of what you're looking at due to, it's actually you changing position. So looking from the small space between your two eyes, looking from one eye to the next eye, that change in position of the observer causes it to appear, for example, that this building is moving. So the building isn't moving. It's that you're looking at your left eye and your right eye. So the understanding was we would see this shift in the objects of the heavens. So the stars, we would see a shift if we on Earth were moving. Since there was no shift, that must mean that the Earth is stationary. So they're right and wrong. The logic behind that is correct. Parallax is right. The only thing is, there is parallax of the stars from Earth. It's just so small that it's not observable from the eye. So at this time, it was not observable. We didn't know that there was parallax from Earth because the distance from Earth to the stars is so huge that the parallax is not observable. So we can't actually see it with the eye. It's way too small. So at the time, this did make sense. If the Earth was moving, they would see parallax. They didn't see parallax, Earth must be stationary. Now we know, of course, the Earth is moving and there is parallax. It's just very, very, very small. Oops, excuse me. So, the problem with Aristotle's model of the universe, with Earth in the center, everything rotating around in those 55 spheres, is that the planets didn't quite fit. And this is because of retrograde motion. So we know that when planets lap each other or pass each other as they're orbiting the sun, they cause a backwards motion, apparent backwards motion from the viewpoint of Earth. So this backwards motion could be observed, but it was not explained by Aristotle's model. So the next astronomer, philosopher, Ptolemy, expanded upon Aristotle's model to try to explain this retrograde motion of our planets, where we see this apparent backward zigzag loop-de-loop pattern of the planets. So he came up with that Earth is in the center, the planets are rotating around Earth. They're not only rotating around Earth, they're rotating in circles around their orbit around Earth. So that would explain, if you follow this arrow here, it would explain how the planet could be moving from east to west, and then have this backwards motion, then continue along its path as it's moving in these circles. So it would look something like this. with the Earth in the center. So Ptolemy said that the planets are rotating around Earth, but they're also rotating on their own small circular paths around their orbits around Earth. So next came Copernicus, who was not totally satisfied with Ptolemy's model. So he was the first one to write, that we know of, to write down and try to distribute knowledge that the sun might be in the center of the universe. So he wrote an essay proposing this idea. He hand wrote it. It had no title, and he often didn't even put his name on it, and was trying to share this knowledge and gauge reactions, because it was very against the church. He was afraid that he was going to be ridiculed or tossed out because of this idea. So he wrote that the Earth rotates on an axis and actually revolves around the sun. So after publishing this initial thought, he wanted to look more into it, spent most of his life finding more evidence, collecting more observations, making more calculations to try and support his idea, and eventually published a book. He wrote a book that finished in about 1529, and it was published in 1543, right after he died. So he had a lot of correct information about the Earth on its axis rotating around the sun, but he still couldn't perfectly explain the position of the planets. So the planets were a big cause for a big problem. So he was able to explain that with the sun at the center of our solar system, as we know that it is, retrograde motion, which is true, is able to explain that backwards pattern that we see in the paths of the planets. So he understood that the sun was at the center. He understood retrograde motion. However, the problem was that using his model and his understanding and his calculation, you could track the path of the planet, but you still couldn't perfectly accurately calculate where the planet was going to be. So something was still off in his calculations and his understanding. So he had the heliocentric universe, which is the sun at the center, instead of the geocentric universe, which was previously believed, geocentric being Earth at the center. But the problem was he was still assuming uniform circular motion. So he was still assuming that everything in the heavens had to be perfect circles. So he recognized that Earth was a planet revolving around the sun. Earth was one of many. And he really changed the view of Earth's place in the universe, and also in that of humanity's place in the universe. So he really changed the fact that we are not the center of everything, the greatest beings of all, by saying Earth is just another planet. There's a bunch more. We're all rotating around the sun the same way. So the thing he still didn't quite understand was that the orbits are not perfect circles. So, and the next important invention, or discovery, I should say, was in 1572 by Tycho Brahe. So he discovered Tycho's supernova. And we're going to get into supernovas later in the course. But the main discovery with this supernova is that he was able to say this star that he found had to be further away than the moon and the heavens. So this was the first time that someone was able to say and prove that stars are at different distances from Earth, and it's not just a big starry sphere around our solar system. So it's not that the heavens are perfect and unchanging there as a giant circle around us. It's actually the universe, which we know is not that perfect painted celestial sphere, which was originally understood. So this was a big contradiction of the idea of the heavens being perfect, being a perfect circle around Earth, around our solar system, and that the heavens are unchanging. So he was able to show that there's depth to the universe, depth past Earth and past the moon and the planets. So Johannes Kepler worked with Tycho Brahe, and after Tycho's death, Tycho Brahe's family didn't want Kepler to continue working with Brahe's material, his equipment, his notes, but Kepler kind of snuck his way in there, took his notes and some of Tycho Brahe's equipment, and continued studying. And thankfully, he did this because he was able to come up with some pretty amazing discoveries. He solved the issue of the planets in 1606. He realized when looking at Mars that the only way to perfectly predict where Mars is going to be, which they should have been able to do with these models, is to assume that Mars is not orbiting in a perfect circle, and it's actually in an ellipse. So he was able to solve the problem of all of these astronomers before him by realizing that the orbit of the planets are not perfect circles. They're very slightly elliptical. So he created the 3 laws of planetary motion and published them. So the first is that the planets are orbiting in elliptical paths. So they're very, very, very close to circular, but they're not perfect circles, which now makes the math work out. So ellipses are on an elliptical scale from 0 to 1. So a 0 would be a perfect circle. So this is a 0.02, so it's very close to being a perfect circle. And here we see a 0.6, which is obviously much more elliptical. So a 1 on the scale would be very, very elliptic. So here is the mathematical explanation for an ellipse. So here you'll see that there's 2 set points in the center. The sum of the red and the blue line throughout is always the same, but the portion that is red versus blue changes as an object rotates around this ellipse. So here is an example of Earth's orbit. So we have a almost nearly circular orbit, but it is still elliptical, so it is not a perfect circle. Pluto is the most extreme elliptical orbit around the sun. It's at about a 0.25. We on Earth are at about a 0.0167. So we are very, very, very slightly elliptical on Earth, but it is still not a perfect circle. So Kepler was the first one to realize and publish that the planets rotating around rotating around the sun are not rotating on perfect circles. So his second law is about the speed of the planets. So he realized that along these elliptical orbits, the speed is not the same throughout. So it's not, planets don't travel at a uniform speed. So if you were to take an imaginary line and allow it to sweep along the orbit of a planet around the sun of equal time, you would see that the planet moves different amount depending on where it is on its orbit. So for example, it takes the same amount of time for the planet to move from A prime to B prime here as it does for the planet to move from A to B. It takes the same amount of time, meaning that over here, the planet must be going slower. And here, the planet has to be going faster in order to cover this whole space. So when the planet is closer to the sun, it's actually moving faster. It is covering more area of that orbit. When the planet is furthest from the sun is where it is moving the slowest. That's Kepler's second law. So here is a GIF, and each colored piece, so each piece, the gray and the navy, each one is covering the same area, but you'll see that you can obviously see the change in speed. So each pie piece here is the same physical area, but since the sun is not directly in the center, we see that when the object is closer to the sun, it covers much larger amount of that orbit. When it's further from the sun, it's covering a smaller amount of that orbit. So the third law that Kepler published relates the distance of an object from the sun to the orbital period, so the time it takes the object to orbit around the sun. So he was able to say and prove that the time it takes to orbit around the sun squared in years, so we usually say in terms of Earth years, is equal to the distance from the sun cubed. So the distance, they are related in that when the distance goes up, the orbital period is going to go up, and vice versa. So we can see that here. As the distance goes up, the period goes up on this very nice graphed line here. So it's it is exactly proportional. Period squared is equal to the area squared. The area cubed. So you can see that here. An object that's closer to the sun is going to orbit around the sun quicker. So its year is going to be less. It's going to take less time. An object further away from the sun is going to take a much longer time to orbit around. So its year is going to be longer. And there's a direct relationship there. So these laws, which we call Kepler's laws of planetary motion, 1, 2, and 3, were published in 1627. So the biggest, most important aspect of this is that he could predict the motion of the planets, where the planets would be, with between 10 and 100 times more accuracy than could be done before. So this really helped prove and solidify that he was correct. So next came the invention of the telescope. It's actually around the same time. It was invented in Holland by an eyeglass maker. He created what he called the looker, and it could magnify something 2 or 3 times, so up to 3 times magnification. So he was actually awarded the very first patent for a telescope. So Galileo took who took this next idea. Took that same idea, created his own telescope to study the sky. And Galileo is considered the grandfather of astronomy. You will see why in a couple of slides after I go over all the things that he discovered. But he made 3 very important discoveries. First, with this telescope that he created. So firstly, he realized the moon is not perfect. So the moon is not a perfect heavenly body. It has craters. It has mountains. It's the first time that we could see what's on the surface of the moon. He also was able to say that the Milky Way is made up of many, many faint stars. So the Milky Way has many more faint stars than were previously thought because he could now see them with his telescope. And he also discovered 4 new moons. Well, he thought they were planets. So he discovered planets orbiting Jupiter, but we now know that they are moons. So here is a copy of some drawings dated with his observation of Jupiter and its moons. So he was able to show the way that these he called them planets, but we know that they're moon, the way that these moons orbited around Jupiter. So he proved that these moons are orbiting around Jupiter. They're not orbiting around Earth. So this is even more evidence and proof that not everything rotates around Earth. We are not a geocentric solar system. It's actually the sun at the center. So proving that these planets can orbit around something other than us further proves that the planets are rotating around the sun rather than around Earth. So this is a very big discovery. He also discovered sunspots. So we will talk about sunspots. I think we'll start talking about the sun in week 7 or week 8. So we will talk about sunspots a lot in detail, but there are dark spots on the surface of the sun. So he mapped them day by day, mapped the location of the sunspots on the sun. So he was actually able to prove that the sun is a sphere and that it's rotating. So using the motion of these sunspots, he was able to prove that the sun itself is also rotating. And he discovered, I'm telling you, grandfather of astronomy, discovered that Venus goes through phases like the moon. So Venus, from our point of view, goes through phases similarly to the moon, where we can see different portions of Venus illuminated. So that would not make sense in Ptolemy's model of the universe with the geocentric model, which would look something like this. If here we have Earth, here we have Venus, there is the sun, we would always see the same side of Venus. We know, in fact, or we would always see the same illumination of Venus, or lack thereof, I should say. When in fact, we have Venus rotating around the sun, Earth rotating around the sun outside of Venus, we end up seeing different phases, similar to moon phases, of Venus, different Venus phases, based on the orientation of Venus, the sun, and us on Earth. So depending on which part of the sun is illuminated which part of Venus is illuminated by our vantage point, we see the different phases of Venus, just like we see different phases of the moon. So this was another very important discovery to prove that the Copernicus model of the heliocentric universe with the sun in the middle was fact. Another huge piece of evidence to show that the sun is in the center of the solar system and that the planets rotate around the sun, not around Earth. So in 1616, the church came to Galileo, and it's the church that ruled at the time, came to Galileo and said he needed to stop studying, needed to stop talking about his findings and ideas, stop spreading his knowledge. His books were banned, and the heliocentric model was kept as a theory. Not a fact. It was not at all accepted. In 1623, a new pope came to power and came to Galileo and encouraged him to publish and continue his studies. So in 1632, he wrote and published a book translated into the dialogue concerning the two chief world systems. So it was a debate type book based on the ideas of Copernicus versus Ptolemy. So unfortunately, it was not loved that he was publishing something that so obviously went against what the church was teaching and believed. So he was sentenced to life in prison, and he lived on house arrest until 1642 for being the grandfather of astronomy. So the big issue with what he published in his trial was that it was a conflict of sort of the two worldviews. So the biblical view that all answers about everything come from faith, come from religion, and then this newer view of the scientist that uses actual evidence, observational evidence. Sometimes this evidence contradicted what was in the Bible or what was believed by the church. So Galileo's trial was really, it's considered to be the birth of modern science, or the birth of using science and evidence and observations to understand the universe. Even though he was sentenced to house arrest and didn't get to publish anymore or work anymore on astronomy and studying space. So he died in 1642. 1642. He died on house arrest with a guilty verdict. In 1979, Pope John Paul II looked at his trial again, and conclusions came in 1992 that he would be forgiven. So Galileo was officially forgiven by the church, but he's still not innocent. So he's still guilty for speaking out against the church, but he was forgiven, which I think is a little hysterical because we know that he was right. So this was 1992. This was almost 30 years ago, like not very long ago, and he is still considered guilty, but he has been forgiven, sort of pardoned. So Galileo passed in 1942, which is the same year that Isaac Newton was born in England. So he made absolutely huge advances in astronomy, mostly in the physics and the math that make up astronomy as we know today. So he made huge discoveries in optics. He was the first to really understand gravity and how it works and how you can use math to calculate gravity. And he invented calculus. So anyone taking calculus, anyone taking pre-calc, you can thank Isaac Newton. He also developed 3 laws of motion, which are very, very, very important to our understanding of the world today. So the laws of motion are about motion of an object and forces that can or cannot act upon it. So the motion of a body, meaning not a human body, but any celestial body, let's say. So his 3 laws allowed for a lot of calculations. So a lot of calculations in future motion. So predicting future motion, looking at how will things react to certain forces. So the first of his laws is a body in motion stays in motion. Also, a body at rest stays at rest, unless it is acted upon by an external force. So what this means is an object that is still on a flat, straight path is not just going to start moving on its own unless it's acted upon by an external force. So unless something pushes it, it's not going to start moving all on its own. If something is in motion, it's going to continue moving until something slows it down. So the second law is that acceleration of anything is proportional to the force that's applied. So this is where the equation force equals mass times acceleration, or F equals ma, comes into play. So he came up with this, or discovered the idea that force is equal to the mass times the acceleration, or acceleration is equal to the force divided by the mass. So the proportionality between acceleration of something and the force that causes it to accelerate. And the third of his laws is about action and reaction. So if one body exerts a force on another body, that second body is going to exert the same exact force straight back at the first body. So one thing pulling on another thing, that second thing is going to pull right back. The only thing is, it is the same force, equal in magnitude but it's opposite in sign because it's now in the opposite direction. So body 1 exerting a force on body 2. Body 2 exerts that same force back on body 1. So same force in magnitude, but opposite in sign. So one would be positive, one would be negative, for example, but they would be the same value. So those are Newton's 3 laws. Very, very, very important laws, the basis of physics. This is just a summary slide here of a nice graphic that I found explaining them. So with these laws, Newton was also able to explain a lot about gravity. So he found all masses attract each other. So everything is exerting attraction force on everything else. The force, however, depends on the size of the objects and the distance between them. So it depends on the masses of the objects and how far apart they are. So it's the same force that causes something to fall from a tree to the ground, same force that pulls the moon to the earth. Just different values based on the masses of the two objects and the distance between them. So he came up with this equation. The force is equal to a constant value times the mass of body 1, the mass of body 2, divided by the distance between them squared. So I found a video on YouTube that I really like the way the scientist explains this equation. So I'm going to show you just a minute or two of this video. If you want to come back and watch the whole thing, because it really is great, I do have the link to it here.
You've been told the story of Newton's apple at some point. The story goes that one day he was sitting under an apple tree in his mother's garden when an apple fell out of the tree. That's when Newton had his grand realization that something was pulling that apple down to Earth. And that led to another idea. What if the apple was pulling on Earth too, but you just couldn't tell because the effect of the apple's force on Earth was less obvious? A few years later, Newton was sitting in the same garden when he had another stroke of inspiration. What if that same force that pulled the apple to the ground could affect things much farther from Earth's surface? Like the moon. It was kind of counterintuitive because the moon orbits Earth instead of crashing straight into the ground like an apple that falls off a tree. But Newton realised that the moon was still being pulled towards Earth. It was just moving sideways so quickly that it kept missing. That was what was keeping it in orbit. If gravity was keeping the moon in orbit, what if it affected the behaviour of any two objects, like a planet orbiting the sun? That's the official version of the story, the one Newton himself used to tell. Most historians think he was embellishing at least a little, but there probably is some truth to it. Whether or not the thing with the apple actually happened, Newton thought that his idea seemed promising. The idea that gravity might affect everything, including orbits of other planets and moons. So he started looking for an equation that would accurately describe the way gravitational force made objects behave, whether it was an apple falling on the ground or the moon orbiting Earth. Newton knew that however this gravitational force worked, it would probably behave like any other net force on an object. It would be equal to that object's mass times its acceleration. The mass part was easy enough. It would just be the mass of an apple, or the moon. It was going to be a little harder to figure out the factors that were affecting the acceleration part of the equation. The first thing Newton realised he'd have to take into account was distance. When an object is close to the Earth's surface, like an apple in a tree, gravity makes it accelerate at about 10 metres per second squared. But the moon has an acceleration that's only about a 3,600th of that falling apple. The moon also happens to be about 60 times as far from the centre of the Earth as that apple would be, and 60 squared is 3,600. So Newton figured that the gravitational force between two objects must get smaller the further apart they are. More specifically, it must depend on the distance between the two objects squared. Then there was mass, not the mass of the apple or the moon, but the mass of the other object involved in the gravitational dance. In this case, Earth. Newton realised that the greater the masses of the two objects pulling on each other, the stronger the gravitational force would be between them. Once he had taken into account the distance between two objects and their masses, Newton had most of his equation for the way gravity behaved. The gravitational force was proportional to the mass of the two objects multiplied together, divided by the square of the distance between them. It had to be a lot smaller, or else you'd see a force pulling together most everyday objects. Like this Rubik's Cube is staying right where it is, instead of being pulled towards me, so the gravitational gravitational force between us must be very small. So Newton added a constant to his equation, a very small number that would make the gravitational force just a tiny fraction of what you'd calculate otherwise. He called it G, and he called this full equation F equals gmm over r squared, the law of universal gravitation. Newton had no idea what number big G would be, though. He just knew it would be a tiny number and put the letter G into his equation as a placeholder. About a century later, Henry Cavendish, another British scientist, made careful measurements with some of the most sensitive instruments of the time. He figured out that G was equal to about 6.67 times 10 to the negative 11th newtons times meter squared over kilogram squared. So indeed, Newton was right about big G having to be quite small. But even though he didn't know the exact value of big G at the time, Newton had enough to establish his law of universal gravitation. He described gravity as a force between any two objects and published his equation for calculating that force. Then Newton took things a step further. Well, technically 3 steps further. About 50 years earlier, an astronomer named Johannes Kepler came up with 3 laws that describe the way orbits work, and those predictions almost perfectly matched the orbits that astronomers were seeing in the sky. So Newton knew that his law of universal gravitation had to fit with Kepler's laws, or he'd have to find some other way to explain why Kepler was wrong. Luckily for Newton, his law of gravitation not only fit with Kepler's laws, he was also able to use it in combination with his 3 laws of motion and calculus to prove Kepler's laws. According to Kepler,
so this equation, it's a pretty big deal in astronomy. If you've taken physics or you are going to take physics in the future, you will definitely be using this equation. It is the equation of mutual gravity. So this is the relationship, the force of gravity depends on the 2 masses of the objects, and the distance between them. So if we look at gravity and the moon, we would know that from Newton's first law, the moon is in motion, so it should stay in motion. So it should be moving in a straight, perfect line. It's not. It orbits around the Earth. So we know that something must be acting on the moon to keep it from moving in that perfect straight line, as the first law says. That force is gravity. So not only is the moon moving, it is moving eastward, it is also being pulled down towards Earth. So that is what keeps it in its orbit. So the moon actually moves 1,020 meters east every second, as it is also falling 0.25 millimeters towards Earth. So it's moving to the east and also falling towards Earth at the same time, but at a rate that is sustained by its orbit around us. So this brings us to the last topic for today, which is circular velocity. So circular velocity is the velocity that is needed in order for an object to stay in orbit around another object. So if we were to launch a satellite into space, we would need it to have, it would need to have enough speed initially, and then we would need it to reach its circular velocity in order to stay in orbit around Earth. Or else it will fall back towards Earth. So if it's too fast, it will shoot out and go too far and will not stay in orbit. It will just go out to space. If it's too slow, it might reach a good height before it falls back down towards Earth. So the circular velocity depends on the mass of the object and then the distance between the object and, say, the satellite. So everything orbiting around Earth or orbiting around anything else is orbiting at its circular velocity. So the object has to reach that circular velocity or else it will fall back towards Earth. So here's a nice diagram of a cannon. So let's say we're shooting a cannon trying to reach that circular velocity. If it's anything less, it will eventually fall back towards Earth because gravity will overtake. So this is how we have geosynchronous satellites. So a geosynchronous satellite is a satellite that is locked in on one location. So, for example, we have weather satellites and GPS and communication satellites, but weather satellites are a good example that are always above the east coast of the US. always collecting data above California. And we are able to calculate exactly where the satellite needs to be so that it is always above a fixed spot on Earth's surface. So as Earth rotates throughout the day, the satellite stays with it, also rotating. So the satellite needs to have a perfect orbital period of 24 hours, just like the Earth. So in order for a satellite to be geosynchronous, have that perfect 24-hour orbit and always stay locked on the same location on the surface, the satellite has to be 42,230 kilometers from the center of the Earth. So it has to be very, very precise. It has to be at this exact height so that at its circular velocity, it will have an orbital period of 24 hours and always be looking down at the same exact spot. So weather satellites, we always know that we'll have coverage in the west coast of the U.S., for example. Communication, we always know that we'll be able to pick up our phone and make a call because we have service. That satellite is always above, for example, the west coast of California. So when we think about orbits, we can think of orbits like a seesaw. So technically, the moon doesn't really orbit around Earth. So if we think of a seesaw, and here we have a girl on the left side here, and she's bigger than the boy that's on the right side. So she weighs more. So you'll notice that they are totally balanced. So they're both hovering in the air. And that's because someone moved the center point of the seesaw. So the center is no longer, the pivot point is no longer in the center of the seesaw. If it was in the center, the girl would go down to the bottom and the boy would go up because she's heavier. So she'd be sitting on the ground and the little boy would go flying into the air. But since the center of mass is shifted, they're nice and perfectly balanced. So things in orbit are the same way. So if they're in a nice balanced orbit, that means that these two objects, let's say the little planet or the little moon and the planet, are rotating around the center of mass, their pivot point. So both this planet and this moon are rotating around the center of mass between them. So this is the same with Earth and the moon. So both Earth and the moon rotate around their center of mass. So the center of mass between the Earth and the moon, where our pivot point of our seesaw would be, the balance point between them, is the point that both the Earth and the moon rotate around. So where would we find the center of mass of the Earth-Moon system? So I'm saying that both the Earth and the moon are rotating. It's not just the moon rotating around Earth, it's the fact that both objects are rotating around their center of mass. As it turns out, the center of mass between the Earth and the moon is actually within the Earth. So instead of being right in the middle, it would be right in the middle if they were the same exact size, same exact mass. They are not. The moon is much, much smaller. So in order to balance, the pivot point has to actually move all the way towards the center of the Earth, that it's within the Earth. So it appears that the moon is orbiting around the Earth. We don't see the Earth also orbiting because the center of mass is within the planet of Earth. So here again is the same timeline that I went over in the very beginning of class. We just covered all of these very famous astronomers and their main observations, their main discoveries, and some of their discoveries we know have now been proven to be quite incorrect, but still very important to understand how astronomy came to be. So I would like to note that I will not expect you guys in class to remember the specific dates or the specific years, but you should be familiar with all of these names and the different things that they were able to prove and show. You won't need to know the years. I am, of course, teaching with the years so that we have some sense of flow and distance between these discoveries. So here is a view of a very, very, very old calendar that based on astronomy or studying the sun. This was a large calendar, among many other things. It was also a place of worship and I believe a tomb. But it was aligned so that through one side of the circle was perfectly aligned with the sunrise on the summer solstice. The opposite side of the circle is perfectly aligned for sunset summer solstice. So this is Stonehenge. It was aligned and built based on the solstices, based on how the sun travels throughout the year. It's dated to be between 3000 and 2000 BC, the age that this was first built.